Good afternoon, ladies and gentlemen. My name is Art Rubio. I am the project manager for Team RoboRonin. RoboRonin is a competitor in the mini sumo competition, which will take place this Thursday, December 10th, in the engineering lab. For presentation overview, we're going to be taking you into the world of mini sumo, and in doing so, we will provide you with justifications of exactly what sort of design process we took, as well as the hardware and software integration for mini sumo. At the end, we'll open up the floor for any questions you might have for RoboRonin. I'll pass it on to Francis for mini sumo.
All right, so thanks, Art. So what is mini sumo? Mini sumo is a competition between two fully autonomous robots. It's similar to traditional sumo wrestling. It takes place in a circular ring. And like other competitions, we have rules and regulations. One, the bot must be fully autonomous, drive by itself, no control from outside sources. And there's a height and weight and size limitation. So the length and width cannot be longer than 10 centimeters. But however, the height can be as tall as it wants. And we do have a weight limitation of 500 grams. And for our project, we have a budget of $500. And now we have Lynn. She'll take it away with the design process.
So for our prototype, our Mark 1 is just the bottom chassis that we print out to test our motor and the wheel. Our Mark 2 is the first complete design, with the two-wheel design. In the front, we have a little scoop so that we can lift the opponent up and then push them easily. Around the robot, we have 8 proximity sensors. We also have 4 reflecting sensors at the bottom. Inside the robot, we have a slot so that we can slide in our custom PCB. On the right-hand side is our model. Since at the moment we didn't have our custom PCB yet, so we just connect off the component with the physical wire so that the company guy can test the code. After some of the design, after some of the tests, we decide to make some modification in our Mark 3. Instead of the scoop, we change it into the flat surface so that we can increase the pushing area. We also add in 2 more proximity sensors. For the PCB design, as you can see along the side of the PCB, we have all the header to connect all the sensor. At the center, we have the microcontroller. Underneath it is the buck converter and also the 2H driver. We also have the LED indicator, the battery started. On the left side is our 360 degree of the robot. We did the paint job in like using the Japanese theme. For the block diagram, we're using the battery with 11.1 voltage to supply the power for the whole system. Since all of the components using the 3.3 volts, so we use the buck converter to convert from 11.1 to 3.3 volt. All of the sensor gonna send back the signal to the microcontroller using the ADC pin, and it's gonna process the information and control the H driver bridge and control the motor. Next, I'm gonna pass the robot to talk about the software side.
Thank you, Lynn. And so for the microcontroller, we decided to go with the STM32F0. This microcontroller has a microprocessor that runs at 48 megahertz, so it's very powerful. The more process power, the better it's going to be, obviously. Apart from this, we decided to go with this because of its availability, of our previous experience with it, and of course because it more than meets the minimum requirements for this project, which would be at least 2 pulls with modulators and 14 analog to digital converters. Next, I will talk about the algorithm. This is the top level design of the algorithm. At very first, before the match even starts, we'll place the robot on the ring, and the robot will be waiting for a start signal. The start signal will come from a remote control. Once the button of the remote control is pressed, the signal will be sent to an infrared sensor placed on the bot. Once the IR sensor receives the signal, then the bot will know that the match has started and it will begin to move. And at this point in time, we'll go from the start state into the roaming search state. And the roaming search state will constantly roam in the ring and actively look for the opponent. We did modify the proximity sensor positions a little bit so that we could strategize with it. This will be talked about later. But for right now, in the roaming search state, if any of the proximity sensors do detect an opponent, then we go straight into the offense state. In the offense state, depending on which proximity sensor detected the opponent, the robot will turn a certain degree until the front sensors are facing the opponent robot, and it will attack it. It will adjust the duty cycle on the PWM in order to make the motors rotate more and increase the speed. If during any of the roaming search state or offense states, the NH is detected, then we'll go into a defense state. In this case, Any action currently being performed will be overridden and we'll back off from the edge because we don't want to lose the match. Next, I will pass it on to Julian so he can type those into pseudocode.
So here's a look at what's happening underneath the hood, essentially, for our sumo. So we have a sysdig. It's an interrupt that is occurring every millisecond, and each time we go into that, we are converting one of our sensors into a digital value. And then also in there, we'll change to get the next sensor. Next, we have a global interrupt, and in here, we're waiting for the start signal at the beginning of the match. So this occurs every 0.1 milliseconds to wait for that start signal bit value to come in, and once we receive it, here in the main, we'll then begin checking our sensors. So over here on the right-hand side with our sensors, we have the 4 reflectant sensors, and those are going to be our first priority, as we do not want to fall off the edge of the ring, and they also are essentially a kind of a backup to our other sensors. They're their last line of defense. Once we hit the edge, we want to get ourselves away from the edge, back towards the center of the arena. Next, we have the 2 front proximity sensors, and those will both, if they both detect the opponent, that means they're directly in front of us in line. We can go ahead and move forward and increase our speed to try to push them out of the ring. Then we have 2 sensors on all sides, the left, right, and back, and with those we can rotate appropriately and get them into our line of sight, and once again push them out. And then with our default, if none of the other sensors detects the opponent, we'll be in our roam state. And so when we're roaming, as previously mentioned, our proximity sensors around the top of the robot are angled downwards, so we can actually detect the edge of the ring before we get there with the lower reflectance. So it gives us more reaction time and can keep us towards the center of the ring. And next we have a short video of showing how some of the code. So you see there when it hit the edge of the ring, it backed away back into the center, keep from falling off. And next I'll pass off to Diane to discuss the sensors more in detail.
All right, so our first problem is we need to be able to detect the opponent. So to do so, we utilize the 10 sharp infrared sensors on our robot. So the way an infrared sensor works is it has a transmitter that emits infrared light. If an object is detected, that light will be reflected back to the receiver, which the receiver will then calculate to the reflected angle and produce a corresponding voltage. As this object comes towards our robot, the voltage will increase, and this can be seen from our voltage gradient. We also have this diagram that represents accurately about how much we're able to see. Our sensors were able to have a 270-degree visual range of the arena, where our visual distance is about 20 centimeters. You can see that we do have blind spots, however, this is pretty much negligible due to the fact that we're constantly roaming. In addition, so to maintain a sensor location within the ring, we have angled the sensors downward at 63 degrees. This not only allows us to detect the opponent, but also detect the surface. So we're able to detect a voltage change when we get close to the ring and then maneuver back accordingly. So as a backup to our proximity sensors, we also use the Fairchild reflective sensors. Now this sensor is a little bit simpler. All it does is it reflects light off a surface, and then depending on how much light is returned to the sensor, voltage is provided. As you can see from our testing, we see the largest voltage change between the black and the white surface, which is great for our purposes. However, we will rely mainly on our proximity sensors. So now that we're able to maneuver around the ring, we actually need to control the robot, speed, and the individual motors. To do so, we have 2 DC brush motor driver carriers. Each motor is individually provided a driver carrier to prevent from overheating, as well as provide separate pulse width modulation duty cycles so we can control the speed. The way a brush DC motor driver works is it has an H-bridge, first and foremost. So 2 PNP transistors are connected to the voltage source, while 2 NPN transistors are connected to ground. Each transistor will have its own diode to protect it from overvoltage, which can occur during stalling moments. This circuit allows for not only the forward movement, but also from the reverse movement. In addition to this, our driver carriers contain a microcontroller, which allows for the pulse width modulation I previously mentioned. This allows us to change the duty cycle on each wheel so that we can make 360-degree spin maneuvers, as well as accelerating quite rapidly. As you can see from our testing of our particular motors and sensors, we are able to achieve approximately 1.5 meters per second linear velocity at 80% duty cycle with pretty substantial voltage draw. Now I'll pass it off to Art, who will talk more about the motor and battery.
So in designing the motors, we had to figure out exactly how much torque can we actually provide with RoboRonin. So with that, we had to assume 2 things. First thing we assumed was a static coefficient of 1 for the polyurethane and the particle board. The next assumption was that we would put 500 grams on the wheelbase itself. So given these assumptions, we did the calculations and figured out that 0.148 newton meters of torque would be established with RoboRonin given those assumptions. Given this value, we were able to purchase the appropriate motor, which was a 29-to-1 gear ratio. That would give us 0.176 newton meters of torque, and it can also provide us with 450 RPM given a 6-volt input. For the wheels, we went with a polyurethane material, which gives us a 0.9 static coefficient with respect to the particle board, as well as an aluminum hub, which gives us 61 grams at the wheelbase for each motor. For the power, we assumed worst case scenarios, so there was 3 assumptions. First assumption was that all sensors would fire off simultaneously. In addition, we incorporated a 1.5 service factor for all the power. In addition, we wanted 3 battles at 6.5 minutes, which is well more than the 2 minutes that is required. So given these assumptions, we also took into consideration the efficiency of the buck converter. As you can see on the graph there, we're operating at 11.1 volts, which puts us on the green mark, and we will maximize at 600 milliamps. This puts us at 80%. So given that efficiency and all the consumption of the power, we came up with 31.64 watts. Given this information, we were able to figure out that we wanted a 3-cell 11.1 volt battery, which is an 800 milliamp lithium polymer. Project management. As we created RoboRonin, we wanted to make sure that we established some sort of milestones that we can keep in track. First milestone was accomplished, which was the integration between the hardware and the software. That was concluded in October 2nd. Second milestone was the actual assembly of RoboRonin, all the components itself. And as you can see, 3 and 4, we had different dates for the milestones. However, it was October 28th, we finished actually milestone 3 and 4. So we tested RoboRonin on the platform to make sure that we couldn't fall off the ring. And we also tested RoboRonin with an RC time constant robot. On November 28th, we finalized the packaging. As you saw earlier, that was the paint job for RoboRonin, making sure that we win in style. I'll pass it off to Francis with the budget.
All right, so as mentioned earlier, we had a budget of $500. This is because we also did a bunch of testing on various sensors, motors, and wheels. We wanted like the best parts for our application. And as you can see, we have a good portion of the money did go to the sensors. We do have 14 sensors all around the robot, and that's because we want to be able to see the whole arena. And Art has a special announcement.
Okay, it's our special announcement. So on Thursday, December 10th at 1 p.m. in the engineering building, E217, we will be battling RoboRonin. So it will be the clash of the world's finest in autonomous robots. So make sure you are there, okay? We will also be conducting matches on Design Day, which is on Friday, December 11th, continuously back and forth all day. Okay, so please stop by. Does anybody have any questions?